Hello everyone, I'm Dr. Rizwana, working as a Professor of Physics in Institute of Aeronautical Engineering. So today we are going to do some numerical problems based on particle in a potential box. Now, already in my video, I have discussed about potential box. So just we'll try to recollect about potential box. So how we'll form a potential box for an electron. So for that, what we'll do first, we'll take free electron and we'll consider one-dimensional motion of free electron. So here electron, it is moving along the x-axis. Then that free electron, it is made bound electron by constructing boundaries. So what are those boundaries? I'll select two regions on this x-axis. And at those two regions, I'm going to apply infinite potential. And those two regions, I'll take it as x is equal to 0 and x is equal to L. So it means that what is the width of the region? Where that width is L units. So if you have such box made for an electron. So as you can know, as we told that first it was a free electron which was moving freely along the x direction. But once we take those two regions of infinite potential, if electron is moving and once it comes to this region of infinite potential, it won't be able to overcome that infinite potential. It get bounced back. Similarly, the same electron, when it goes and when hits this region of infinite potential, again it gets reflected back. So it means that our electron, it is made to stay only in between those two regions of infinite potential. So this is nothing but potential box, and it is also called as infinitely deep potential well. So if we have such potential box, then energy associated with electron which is trapped in potential box, what is the formula given? It is given as En is equal to n square h square by 8ml square. And what is n here? Of course, n is integer, but it represents quantum number. So if you take this formula, En is equal to n square h square by 8ml square. Here n is our quantum number. And we know that this quantum number, actually it's a principal quantum number which will give you different energy levels. And one very important conclusion we have taken for energy associated with potential boxes, instead of having continuous energy levels as given by classical free electron theory, so this equation related to quantum theory, it talks about discrete energy levels. So what do you mean by discrete energy levels? So if I try to take energy levels based on this formula, then we'll draw those energy levels like this. Of course, this is for an electron which is bonded in a potential box, whose boundaries they are given as x is equal to 0 and x is equal to L, and for n is equal to 1. So how we'll represent these energies? So if I consider these energies, so we have a box. This is x is equal to 0. This is x is equal to L. In this we have our electron. Here we have applied infinite potential. And if we try to draw energy levels by taking that expression for different values of n, then we'll have energy levels like this. This is for value of n to be 1, then I have 2, then 3, and then 4. So this is E1, E2, E3 and then E4, and as you can make out that these energy levels are well separated from each other. So it means that energy is not continuous, but only certain particular values of energies are allowed, and that particular concept is nothing but quantization of energy. So this is one very important conclusion that comes from our quantum mechanics, which we have taken from particle in a potential box. And also one more important thing, what we can conclude from this expression is energy of particle which is bound in potential box, it is going to depend upon width of the box. What is L? L is the width of the box. So by making use of this particular formula, we are going to solve some problems. And if we look at this first problem for energies associated with particle in potential box, in this problem, here we are supposed to find energies that are possessed by a particle, and this particle, it has a mass. What is the mass of that particle? It is taken as 8.5 into 10 power of minus 31 kilograms, and this particular particle, it is bound in a potential box. And what is the width of potential box? It is 10 to the power of minus 9 centimeter. So we were given mass of particle and also we were given width of potential box, and we were asked to find energies that can be possessed by that particle. So for that we are making use of this formula for energy whose width is given by L. So here mass is given as 8.5 into 10 power of minus 31. And what is the width of the box? Of course, it is given centimeter. We need to convert into meters. So what is that conversion? So 1 centimeter is 10 to the power of minus 2 meters. So if we substitute, then it comes out to be 10 power of minus 11 meters. We know value of H. Now, in order to find energies, I'll start with the ground state energy by substituting N is equal to 1 in this formula. So, if we substitute N is equal to 1, then E1 will come out to be, of course, formula is N square H square by 8m L square. So, in place of N, I'll substitute 1 square. 1 square is obviously 1. And then H square divided by 8 into mass into square of width of the box. So, if we do it, then we have our energy in joules, and what is that value we got? 6.4 into 10 power of minus 16 joules. Now this is our ground state energy level. Because here we were asked to find energies, then we'll try to find one more energy level, that is E2. So E1 is our ground state energy level, then obviously E2 will be first excited state, E3 second excited state, E4 third excited state. So we'll try to find the value of first excited state by substituting N is equal to 2. And here, one thing what we have to notice here is when I substitute N is equal to 1, then even it comes out to be H square by 8m L square. And if I substitute N is equal to 2, I think it will come out as 4 H square by 8m L square, which is written as 4 of E1. So we'll get it as 4 of E1. And similarly, what is the value of second excited state? It will become 9 of E1. So once we know ground state energy or minimum energy, which is E1, then easily we can find values of next excited state. So obviously our first excited state E2, we can write it as 4 of E1. So 4 times the energy of ground state, which is 6.4 into 10 power of minus 16. And if we simplify, it comes out to be 258 in 0.268 into 10 power of minus 16 joules. Then going for second problem, find the lowest energy of an electron confined in a square box of side 0.1 nanometer. So here also we were given width of the box. And what is the width of the box? It is 0.1 nanometer. So nano is 10 power of minus 9 meters. And of course, we were talking about electron. What is the mass of electron? 9.1 into 10 power of minus 31 kilograms. And we know value of Planck's constant 6.6 into 10 power of minus 34 joule second. And we were supposed to find lowest energy. So lowest energy means we were talking about N is equal to 1, lowest value of quantum number. And what is the value of quantum number lowest value? It is 1. So we cannot take N to be 0. It is not permitted because motion of particle is sustained. So that's why we have to start our N value from 1. So obviously our lowest energy will be E1. So if you substitute all those parameters of H, mass and of course width of the box, then our energy comes out to be 60.307 into 10 power of minus 19 joules. Then coming to third problem. In third problem, we were given of course a one-dimensional potential box. And here also we are dealing with electron. And we were given width of the box as 1 into 10 power of minus 10 meters. And here we were asked to find ground state as well as first two excited state energies. So what is the mass of electron? It is 9.1 into 10 power of minus 31 kilograms. Width of the box is 1 into 10 power of minus 10 meters. Okay, and it is already given in meters, so we don't have to convert it. We know value of H. So first I'll try to find ground state energy. So we can find ground state energy by substituting N is equal to 1 in this formula. So if I take it, then I'll have my ground state energy as 0.6 into 10 power of minus 17 joules. Now once we know ground state energy, so it will be easy for us to find the next two excited states. So we were, what do you mean by next two excited states? So after ground state, if we go for two more excited states, then we have to substitute N to be 2 and N to be 3. And we know that first excited state E2 is 4 times the ground state energy. So once we have calculated this, so it will be easy for us to find any excited state value. So this first excited state, it comes out to be 2.4 into 10 power of minus 17 joules. And whereas for second excited state, E3, it will be 9 times E1. So it comes out to be 5.4 into 10 power of minus 17 joules. Now here, again we were given width of the box, which is 4 into 10 power of minus 10 meters. And again we were talking about electron, and we need to find minimum energy. And we know that for minimum energy, again we have to take n is equal to 1. In place of h, we'll substitute as 6.6 into 10 power of minus 34 divided by 8 into mass of electron is 9.1 into 10 power of minus 31 into what is the width of the box? Width is given as 4 into 10 power of minus 10. So if we do it, this is the value of energy in joules. Now here, of course, we were we were given wavelength, like we have kinetic energy value, which is 1.5 times rest mass of electron, and we were given mass of neutron, mass of electron, and velocity of light also given, and we were asked to find wavelength of matter wave. So here, first, because we were given kinetic energy value, which is 1.5 times rest mass of electron. So what is the rest mass of electron? 9.1 into 10 power of minus 31 joules. So we know kinetic energy is half mv square, and from this we can find velocity like this. And what is the mass of neutron? It is 1.67 into 10 power of minus 27. So if we simplify this value, we'll find velocity. And once we know velocity, how we can find de Broglie wavelength? It is given by h by mv. And one more alternative formula is also there. Once we were given kinetic energy, we can find it as square root of 2me. So from this, we can find kinetic energy by substituting value of Planck's constant, 10 power of minus 34 divided by square root of 2 into, here we have to substitute mass of neutron, which is 1.6 into 10 power of minus 27 into what is the energy given? 1.5 times mass of electron. And what is the mass of electron? 9.1 into 10 power of minus 31 kilograms. So if we do it, what is the de Broglie wavelength associated with matter wave? It comes out to be 9.76 into 10 power of minus 6 meters. So today we have done some problems based on discrete energy levels associated with particle which is confined in a potential box. So thank you. I'm going to end my session here.
Like, share and subscribe. Hit the bell icon for more updates.